I'm pleased to say we've got Cendi Dana with us tonight, who is a final year PhD student here at the University of Edinburgh, working on geochemistry and geochronology. And he will give us
clicking the screen again, just
some aspects of those sciences related to a VMS system in Scotland, which is at Kerry Road. So hand over now to Cendi. Thank you.
Right, thank you, Alistair. So yeah, thank you everyone for coming on this talk. Thank you, Edinburgh Geological Society, for giving me this opportunity to share our project on Kerry Road deposit. So this project was actually co-funded by Edinburgh Geological Society and Glasgow Geological Society, as well as from the Geological Society of London, with a little bit of top up from Galantas Gold for the geochemical work. And we also got like a support from NHM London for the chemical analysis. So yeah, so on today's talk, I will be presenting or sharing the result from our fieldwork. So we did a fieldwork, I think it was 2023, if I remember correctly. Yeah, it was last 2 years ago. And since then, we've done several lab works, including lithogeochemistry, petrology, bunch of mineral chemistry work, and most recently, an undergrad student did a field magnetic survey in the region, and which I'm also going to presenting today. But also before we delve deeper into the Geological stuff, I will also briefly going to talk about what VMS deposit is actually, and also a bit of introduction on the importance of the significance of VMS deposit in terms of or in relation to UK critical mineral strategy. Right, so oops, too far. That one, yeah. So as I mentioned, I will start the talk today with a little bit of a context about critical metal stuff. So as probably we know that with the current demand of metal due to the global energy transitions, electrification and stuff, the demand of metal is rising rapidly. And in the UK alone, the demand of copper, for example, will expected to be double by 2035. And quoting from the Minister for Industry of the UK, so the government said that our strategy sets out how we will grow our domestic production and use our international partnership across the globe. And this create like a clear challenge, but also some sort of like an opportunity for geoscience to play a central role in supporting responsible resource development. And this slide actually highlights the scale of the challenge. And for example, in the modern society, the average lifetime, each person consume more than like a million kilograms of minerals, metal and fuels. And well, this example is from American survey, but I would assume it's roughly going to be similar across the world. So, and then here also we can see that as the demand through the years in the future, like the demand of copper, this is the example from copper, the demand will be like rapidly increasing. And here we can see that it's got to to fulfill this demand, the mining requirement is also going to be like this high. So we need like roughly up to 25K million ton of copper to be produced to reach this target, basically. And then a common questions among us will be like, how about recycling rather than doing a mining? So based on the modeling that have been done by the World Bank, even with 100% of recycling rate, which currently we can't do that, we are currently like maybe around like half recycling rate. So it's not going to be, even if you are going to recycle the whole thing, like for example, the solar panel or the wind turbine, you can't even like recycle the whole thing. You will only be able like just get like 50% recycled stuff from that. So from the model that have been done by the World Bank, even with 100% recycling rate, it's not going to meet the expected amount of metal that we need to reach the target of green energy transition, basically. So we definitely need a new mine or new mining to be open in the future just to fill all those targets with the energy transition and all those electrification and stuff. And as part of the UK government critical metal strategy, in the UK itself, the government established the UK Critical Minerals Intelligence Center. And this CMIC have done a bunch of work, mostly providing a technical report. And one of them is this UK Critical Raw Material or CRM prospectivity across UK. So from this map, we can see that there are several regions across the UK that has a high prospectivity or potential for critical raw materials. And one of them is actually here in the north, and this is actually Lochmary region, or it's near Gairloch, basically. And this location is going to be like the focus of my talk today. So yeah, and then as I mentioned in the beginning, so the talk is going to be about VMS deposit in Gairloch. So, but before we're going into the result of the work that we have done for the past recent years, I'm not sure if everyone here are like familiar with the term of VMS. I'm not sure. Actually, Steve gave the talk last November, I think. November or December about this kind of deposit. So if you still remember, that'd be great. But otherwise, yeah, I'm just gonna give like a little bit of introduction again about VMS deposit. So VMS deposit, or it stands for volcanogenic massive sulphide deposit, is a syngenetic massive sulphide deposit. It's we can think that as a ancient equivalent or analog with a black smoker or a hydrothermal fan system that we found on the seafloor, something like this kind of illustration, basically. And yeah, this deposit is formed in submarine volcanic environments, can be in moor or back arc or volcanic arc. And usually this kind of deposit is classified based on the type of the host rock, something like bimodal mafic, bimodal felsic, paletic mafic, and stuff. But some people also doing the classification based on the type localities, such as Kuroko in Japan, which is actually bimodal felsic, or Cyprus type VMS in Cyprus, which is actually mafic hosted VMS. And the Beishi type, which is paletic mafic, and also Bathurst type, which is felsic siliciclastic in Canada. And this deposit is like the genetic model, or like the deposit model of this deposit is really fairly simple, I would say. You have this kind of illustration where you have like what we call footwall underneath the massive sulphide lines. So the red is the massive sulphide lines, the main ore body that we want. And then underlying these ore lines is what we call footwall units. And in this part of stratigraphy, it's usually characterized by magnesium-rich metasomatism, which is the signature of the feeder zone. And in this feeder zone is also characterized by this kind of mineralization, which is copper-rich stringer or stockwork. And this feeder signature is usually people targeting for exploration. And then on top of this zone, we have this ore body. And then overlying the massive sulphide is usually a thin layer of what we call exhalite. Usually it's like an excess fluid from the hydrothermal fluids. So it can be like a silica-rich layer, or it can be like a barium-rich kind of layer, something like mix of siliceous hydrothermal fluid with the seawater stuff. And overlying that, it's going to be the hanging wall units, basically. It can be a mix of sedimentary or volcanic clastics. And yeah, the massive sulphide is going to be something like this thing. It's called massive sulphide because it's kind of massive. So that's what we get the name. And then yeah, again, the underlying it's something like this big actually. And yeah, like why do we care about VMS deposit? So VMS deposit is actually a really important deposit in terms of supply for zinc and copper. So currently, VMS has been supplied up to 22% zinc and 6% copper in the global metal production. So it's quite significant. And this kind of deposit is usually polymetallic in nature. So you can find like a bunch of metals in one deposit. You can have like copper in the feeder zone or the stockwork. And then in the massive sulphide, you have lead, zinc, silver, and stuff. And then with this current energy needs and stuff with critical metal, you can also find some trace metals, something like cobalt, selenium, bismuth, tellurium, gallium, germanium, and stuff in this kind of deposit as well. And this kind of deposit also have the potential for long-term production. It is because VMS deposit usually found in a cluster where you can find multiple ore lenses in the close proximity. And total past production and current reserve of VMS to date is nearly 14 billion tons. So it's quite a lot. And that's basically a general characteristic of VMS deposit. But in Kerry Road deposit, the VMS has been metamorphosed into amphibolite-facies. And so what happened if you metamorphose a VMS deposit? In a good side, metamorphism can recrystallize the ore body. And when you recrystallize the ore body, everything becomes coarse grain, including the sulfides. So usually in a massive sulfide deposit, the sulfide grain is very small or really fine grained. But when you metamorphose that, everything becomes really coarse grain. So that's going to be beneficial for in terms of the processing and stuff, because everything is become coarse grain. And then by the metamorphism can also release the trace metal that was included or trapped within the main sulfide minerals. Like, for example, in the pyrite, usually containing lots of trace metals like cobalt, nickel, silver, bismuth, and stuff. But when it's metamorphosed, all those trace metal will be released and remobilized and then form a new sulphide facies. And then the metamorphism and deformation can also cause the ore body become slightly more thicker, especially in the hinge zones of the faults, as illustrated in this bit of a diagram. However, the metamorphism can also cause a little bit of trouble. Because the host rock or the footwall or the hanging wall was affected by hydrothermal alteration before the metamorphism happened. So imagine you have like some sort of argillic alteration or like clay-rich alteration, and then you metamorphose those things into high-grade facies like amphibolite or granulite-facies. Everything becomes something like gneisses or schist. And when you do the core logging or description of the hand specimen sample, it might be similar to something that was coming from sedimentary rock, which has like paleolithic rock basically, because it was originally lots of clays because of the alteration and stuff, but it was actually volcanic, so that might be cause a little bit of problem. So here I put like the same protolith can be represented by several distinct metamorphic units due to the alteration before the metamorphism, or it's the other way, different alteration zone, because in VMS deposit, the alteration zoning is usually relatively simple, and people use those kind of zoning pattern as a exploration factor or guide to find the ore body. But then now everything is metamorphosed, everything become homogenized, and then all those alteration zoning now is obscured, and then the rocks or like the metamorphic rock that you found is now become like mineralogically similar with bunch of schist and gneisses. So yeah, that's going to be the challenge for the exploration. And that's why the discovery rate in metamorphic terrain for VMS deposit is relatively low, especially in high grade metamorphic terrain. It's usually around like 6 to 11% discovery rate compared to VMS deposit in like low grade metamorphic terrain such as green schist or zeolite facies. And yeah, so that's why when we trying to do the exploration in a metamorphic terrain, we have to see, instead of just looking at the whole rock composition, we need to see through the metamorphic mineralogy to identify the protolith, whether it was previously basalt, rhyolite, or it was sediment, and also to distinguish different alteration zone, because the mineral is still preserving all those alteration signature, and also trying to establish a robust geochemical or mineral factor to find the main feeder zone or the ore body. So now let's take a look on the Kerry Road deposit. So as I shown in this kind of map earlier, so Kerry Road is located here quite in the north, and this deposit is a mafic hosted VMS deposit, or the company previously classified this as a Beige type deposit. And this deposit was discovered by Consolidated Goldfields in the 70s. They drilled around 87 holes over 9,000 meters, basically. And then the preliminary resource estimation, which have been done like a while ago, like 25 years ago, it's around 500 kilotons at 1% copper, 0.5% zinc, and 1 gram per ton gold. But there's no commercial exploration has taken in place since then until 2018 when the drilling by Green Ore Gold Corporation confirmed the presence of mineralization by intersecting 17 meters at 1 gram per ton gold, 0.9% copper, and 0.6% zinc. And then most recently, the exploration continued by Galantas Gold. They've done a drilling program in 2023, and they have identified a mineralized trend within a strike of over 1 kilometer with a depth of 250 meters. And this is the result of drilling by Galantas Gold. So they drilled 5 drill holes distributed or kind of clustered around here, basically. And the result is actually quite good. Some of them has like really high grade gold. Some, for example, this hole has like a 35 meters at 0.7% copper, 0.5% zinc, 4.4 gram per ton gold. And the UK Critical Metal Intelligence Center also classified this region as a potential region for a cobalt resource, actually. And then, so that's why Galantas Gold also analyzed the cobalt content from the rock. And the cobalt content is range from something around 70 gram per ton to 300 gram per ton. So it's quite varied in terms of the grades. And this is some of the example of the outcrops that we found in Kerry Road. So this is the main massive sulphide ore body or massive sulphide lens outcrop that we found in the location. And Galantas Gold analyzed this outcrop, and it has this kind of grade. It's around 1.6% copper, 2.3% zinc, and it's really high grade in terms of the gold. It's up to 4 gram per ton gold. And then nearby from this location, there is also like a smaller, massive sulfide outcrop. And the grade is slightly different. We have a higher grade of copper, up to 5%, but the gold grade is slightly lower. It's only 2.2 gram per ton of gold. And then we also found some ironstone outcrop. Some people call it banded iron formation. It's not like the typical banded iron formation that you expect with this kind of like banded jasper and iron magnetite stuff. It's more like it's kind of, you have the bedding, but it's basically consists of lots of magnetite and hematite. So it's kind of, I prefer to call it ironstone. And Galantas also analyzed this stuff, and it's about 34% iron, and it's only 0.2 gram per ton gold, so it's really low. Well, it's just ironstone. And this is also some of a sulphide mineralization that they found near the road cut. And they analyzed this bit, and it has a little bit of gold, up to 0.9 gram per ton of gold. And now let's take a look at the geology of the region. I might be not the best person to discuss about the geology of the area because I'm not from the UK, and I haven't done anything much about the geology of the Scotland. In fact, my PhD area is in Australia, so if I say something slightly different, please forgive me. So, but if you want to understand a little bit more of the region, probably the best person to ask maybe Steve or Phil, who's done a lot of work in North Scotland, basically. But generally, the region is part of the Lewisian complex, which mostly consists of Archean basement to early Proterozoic rocks. And this region mostly metamorphosed into amphibolite-facies around 1.8 to 1.7 GA, which called as the Luxfordian event. And so the Kerry Road deposit is located here, and then it is actually part of Loch Mary group, which generally can be divided into two parts, which is the Gairloch schist belt, which is where the Kerry Road is located, and then the other part is the Loch Mary schist belt, which is somewhere here. And then the region, especially the Gairloch schist belt, is intruded by 1.98 GA metagranitoids, and then cross-cut by scory dikes, and then it also has some metashamites, which yielded an age about 2.0 GA from the detrital zircons. So now let's take a look a little bit more into the local scale. So this is the geological map of the Gairloch. The problem with the geological map, there are several versions of geological map in the region. At least so far that I can find is 3 versions, and this is I guess is the oldest one from Jones et al. 1987. It's actually not bad. Records most of the unit that we found in the field. So remember that I showed you the massive sulphide outcrop. It is actually right here, which is nicely recorded by Jones et al. And then, so this deposit is actually located within this, what they call quartz mica schist, which we're not really entirely sure during the field work which rock that is in the field. But we do find this hornblende schist in the field quite easy. And we also found this outcrop, which is the honorary basite, which is nicely cropped out near the road cut, basically. So, and Jones et al. Also mapped several ironstone across this region. So the black stuff is actually the ironstone that I showed you earlier, but they call this unit as a quartz magnetite carbonate schist. But in other map, they call it different things. So it's slightly confusing for me. And yeah, so this ironstone stuff is actually found across the boundary between this hornblende schist and the Fowerdale schist. And they also map several sulphide lens within the honorary basite, which is right here. But during our field work, we didn't visit this region. We only focus on the Kerry Road, which is interestingly, it's not recorded or mapped by Jones et al. About the distribution of the sulfides across this area. And yeah, as I mentioned, this is another version of geological map in the region. So this one is from BGS. And as I mentioned again, they call the unit slightly different. Like the beef or the ironstone stuff, they call as a quartzite schist and metacarbonate, which is completely different thing. So yeah, that's the problem. And this is the most recent map by Harry Hare, an undergrad student from Leeds, who did a structural mapping and analysis on the region. And so he did like a really good job doing like a detailed mapping, but again, it's slightly different. And yeah, they have, what is it? So, well, he recorded the mineralization, which is really nice here, but they have this amphibolite and then quartz mica schist and metaquartzites, which is, yeah, it's slightly different with the one from PGS map. But yeah, that's, yeah, for those reasons, like we have so many different kind of geological map. We plan to do our own map just to confirm which one is like better, I guess, because it's at the moment it's really hard to do the interpretation because of this very different version of a geological map. Oh yeah, in this map as well, this here we plot all the samples that we collected during our field work. So the samples that we got from the Andreri basin is right here next to the road. And then we also grab samples of ironstone, and then we grab the massive sulphide lens, and then we grab bunch of samples from the recent drill core from Galantas as well. So the drill core is actually right here. And then we also grab a couple of samples, what we called as a garnetiferous horizon. So we found like a really interesting rock that has really like lots of garnet in it. And it's only like a really thin layer, but it's really extensive. So we're trying to find those or trying to map those garnet bearing horizon. And then like so far we can only find 5 points of this horizon, but maybe in the next field work season we will try to find a little bit more along this region, because we want to try to analyze those garnet as a factoring tool towards the massive sulphide, basically, which is going to be the stuff that I'm going to talk about today. So this is the work from Harry 2022. Like, so as I mentioned, he did the structural analysis. Basically, the structural geology of the region is very complex. But in general, he what to say, like summarized the structural evolution into 3 main events. So the first one is represented by a progressive folding with the east-west compressional regime along a northwest-southeast subduction zone. And the second event is kind of slightly changing the direction of the stress. So it's turned into north-south trending, or like the main stress is from north-south, which is resulting in a dextral shearing. And then the last event is juxtaposed units northeast of the Kerry schist belt against the Kerry Road deposits. This is the thing, hopefully it's simple enough to illustrate the structural evolutions of the Kerry Road deposit, which, to be honest, for me is still confusing. And now let's take a look on some shiny stuff. So this is the several drill core samples that we collected. So as we can see here, that the massive sulphide, even in the drill core, we can see like a really intense deformation, as illustrated by this like tight folding within the massive sulphide ore body. We have also observed some like what is it, porphyroblasts of, I think it's quartz with a pressure shadow filled with the sulfides. And this is a copper stringer from the footwall, slightly deeper in the footwall part. And then from the petrographic observation that we've done, we can see that the massive sulphide is mostly composed by pyrite, pyrrhotite, chalcopyrite, and sphalerite, as we can see here. And then from the massive sulphide outcrop that we found, because it's on the surface, it got like some lots of oxidation. That's why all those chalcopyrite turns into secondary copper, become something like cophlite and chalcocite as well. And the pyrite, it's also oxidized and turns into goethite, basically. And then there are several ore minerals that has been reported by Jones, such as marcasite, galena, and native gold, but we didn't observe in our samples. Maybe we just grabbed the wrong samples, I guess. Drummond et al. In 2020 also did some sulfur isotope analysis, and the result is range from -0.8 to 2.1, which is very typical of magmatic or volcanic derived sulfur, which is also a typical signature of VMS deposit. So nothing really special, basically. And this is the petrography of the host rock that from the drill core samples that we collected, and some outcrops as well. So this is from the hanging wall unit. So the hanging wall is basically the overlying rocks on top of the massive sulphide. So the hanging wall is mostly amphibolite, and it consists of mostly calcite, quartz, and chloride alterations. We can still find a little bit of a mineralization within the hanging wall, especially the one that has like in contact with the massive sulphide. And this is what we can find. It's a little bit of mostly pyrite, but a little bit of sphalerite and chalcopyrite. And then we also collected some amphibolite as part of, so this is basically for part of the hornblende schist from Jones' map. So, and we interpret this as a part of the hanging wall as well. And then it's basically like a very normal amphibolite, I would say. So it's basically just bunch of hornblende and then a little bit of a quartz and calcite in it. And then we also analyzed the BIF, or the ironstone, and as expected, it's just bunch of magnetite in it. But we also found a little bit of pyrite and a little bit of quartz and chloride within this BIF unit. And then now we're going into the footwall, which is the rock below the massive sulphide. So the first footwall unit that we identify is another amphibolite, but the difference between this footwall amphibolite with the hanging wall amphibolite is the alteration. So in the hanging wall amphibolite, you have more carbonate alteration, which is kind of related to the seawater related alteration process. But in the footwalls amphibolite, the alteration is only like chloritic. And this unit also has some sulphide mineralization, and it's mostly chalcopyrite, a little bit of pyrite, and the mineralization is, as I mentioned earlier, is mostly stringer or stockwork kind of mineralization. But also we observe some sulfides that form along the cleavage of the muscovite, something like this bit, basically. And yeah, this unit is also heavily deformed, as we can see here, like the folding or like the granulation feature within this unit as well. And then the second unit of footwall is biotite quartz chloride amphibolite. So another type of amphibolite, but this part has more biotite and quartz, and it's cross-cut by several like thin calcite veinlets, basically. And then this is a bit more deeper from the previous amphibolite. And then in this unit as well, the mineralization is kind of still similar, but we also found some pyrrhotite and mostly ilmenite. But the ilmenite is a metamorphic product, not part of the hydrothermal system that related to the VMS mineralization. And then the deepest footwall unit that we found is this amphibole biotite quartz schist. So it's now become a lot of quartz, biotite, a little bit of amphibole. And we also found some garnet in this unit as well. And we interpret that while those amphibolites, we certainly show that it was originally basalt, basically. But for this unit, the preliminary interpretation is metasediments, basically, as we found, like, as we can see here, like we have lots of quartz and biotite, which is unlikely derived from the volcanic. And this is the garnetiferous unit that we found that I mentioned earlier. So this is the best outcrop, I would say, of this unit that we can find. The garnet is not that obvious, but well, it's quite fine grained, but it's a lot. So basically, all this in this stuff, it's like full of garnets, but it's just like tiny, but it's a lot. And the garnet is something like this. So here from the petrographic observation, you can see like all those porphyroblast garnet, and it's quite a lot throughout this unit, basically. And we are still not sure what this unit is actually, what is it? As part of the system, like, is it part of the hanging wall? Is it part of the footwall? Or is it something else? We are still not sure, because we still struggle to like correlate this unit with other unit, basically. And in this unit, well, this unit, if we see this petrographic image, it has a lot of quartz, but it also has a lot of chloride after amphibole. So it's kind of like a complicated, basically. But if you have any idea later, we can discuss about that. So. And this is the honorary basite outcrop near the just next to the road cut, basically. So we sample this. There's a little bit of a sulphide mineralization in this bit, the rusty looking bit in this one. But so we sample both the sulfidic stuff and then the like slightly fresh. It also cross-cut by quartz vein. But the quartz vein is not really mineralized. It's just barren quartz vein. It's probably metamorphic related. And if we analyze or if we observe under the microscope, it has a bunch of hornblende, a big garnet as well. And then the sulfidic stuff here, it has a bunch of euhedral pyrite, right? Something like this, and also lots of chalcopyrite. And again, similar to the garnetiferous unit, we are still unsure about this honorary basite. Like, is it part of the hanging wall or is it part of the footwall stratigraphy? But it's in the different, what is it? Different stratigraphic horizon or belt. So yeah, it could be different systems, or it could be the same big systems, but we're still not sure. And then from the bulk rock geochemistry, all those amphibolites, as I mentioned, are metabasalt originally. So all of those amphibolites basically clustered around here, which is also consistent with previous work from Drummond et al. And then the garnetiferous unit is actually plotted here. So it's geochemically, it's similar to metabasalts, but it also containing lots of quartz. So yeah, again, confusing. And the deepest footwall unit that I mentioned earlier that we interpret as metasediments, well, it's not supposed to plot in this diagram because this diagram is false. It's for volcanic stuff, but I just plot it here just for the convenience. It's right here, and it's actually consistent with the composition of the Lochmary group metasediment. So we can ascertain that this is probably metasediments or in origin, basically. And then yeah, this is the massive sulphide and partly mineralized hanging wall amphibolite. Yeah, because it's heavily mineralized, that's why it's randomly plotted here, basically. And so we also plot the data in the box plot, like the alteration box plot. So this kind of diagram is usually used for alteration factor in a VMS deposit. So the proximal alteration trend, or like the feeder trend, feeder signature, is usually has this kind of trending, which is kind of consistent with the footwall amphibolite alteration trend. And then the hanging wall alteration trend is going into the other way. It's going to this way, which is more like a carbonate related alteration, which is going to make sense because it's affected by those seawater alteration and stuff. And then the the metasediments is plotted here in the least altered box. So I guess this was not part of the volcanic host rock that associated with the VMS mineralization, probably. And we also analyzed the rare earth element, and here again, the metasediment stuff, the deepest footwall units, it's again consistent with the Lochmary group metasediments. And all those amphibolite units are generally like, it's fairly consistent. It's kind of flat, very typical of tholeiitic basalt signature. The only thing that is different from metabasalt is Andrary basite, which has a positive europium anomaly here, whereas the rest of the amphibolite that we found is basically showing a negative europium anomaly. And then the hanging wall basalt is also kind of flatty rare earth profile here. It's kind of similar as well. So it's tholeiitic metabasalt signature, basically. And then the BIF unit, or the ironstone unit, we also analyzed the rare earth. So the purple stuff is the BIF. And the rare earth profile is kind of consistent with the regional BIF that has been done by a previous study from Meager in 2024. And yeah, this is the massive sulphide as well. And it's because it's basically sulphide, so that's why it's really low in rare earth. But interesting stuff that another interesting stuff that we can note here is the negative cerium anomaly here that consistently observed in the massive sulphide, partly mineralized hanging wall amphibolite, and then the BIF. So this negative cerium anomaly is usually associated with the seawater related alteration. So it's kind of makes sense because the massive sulphide is like on top of the deposit, right? So it's affected by the seawater, and then also the hanging wall and the BIF. So because assuming that they were formed on the seafloor, so that's why it's affected by the seawater alteration. And then we also done a little bit of mineral chemistry work. So this is the first mineral that we analyze is chloride. So Steve gave a talk on this bit a while ago. And basically what we can tell from chloride chemistry in a metamorphosed VMS system is people usually use the iron-magnesium ratio as a factor towards the feeder zone, basically. But when you metamorphose this system in a high-grade facies, those iron-magnesium doesn't work anymore. So instead, the iron-magnesium in chloride now strongly controlled by the bulk rock composition. So if your profile was really high in iron, so your chloride will have those signature. And then it's also the other way. If your profile has a lot of magnesium, your chloride will be magnesium rich, basically. It's kind of useful if you can find the magnesium rich alteration, which is the signature of the feeder zone. But if it's not, if the magnesium rich alteration is not, detected or identified, it's going to be slightly complicated, especially if your previous rock already has a lot of magnesium, so it's going to complicate everything, basically. But another thing that we found interesting from chloride chemistry is fluorine and manganese. So as we can see from this box plot, the fluorine and manganese in chloride consistently increasing, so like systematically increasing towards the massive sulphide ore body. So the red is the massive sulphide ore body. And then as we can see here, like, so this is the footwall, and then the blue is the hanging wall, basically. So as you go towards the massive sulphide mineralization, the fluorine and the manganese in chloride both consistently increase. And then this is based on the deposit that, from my PhD in King in Western Australia. So we're trying to reproduce this kind of pattern in Geological, and the result is slightly different. So the fluorine is mostly below detection limit. That's the problem. So we can find that beautiful pattern anymore. But the manganese is kind of, it has those increasing trending pattern towards the massive sulphide. So this is the footwall stuff, and then this is the hanging wall, and then this is the garnetiferous horizon, basically. So here we can see that the footwall amphibolite has those kind of increasing manganese pattern towards the massive sulphide mineralization, and then drop in the hanging wall, which is kind of similar with the trend that we observed from in the previous slide. But the problem here is with the deepest footwall unit that we have is kind of the same magnitude with the like uppermost or the immediate footwall, like in terms of the manganese content. Also the garnetiferous horizon is also similar, like in terms of the concentration. So I'm not sure what made this happen, but my preliminary interpretation is probably this manganese, like relatively high manganese in this part of rock was probably derived from the original protholith. So the protholith was, because this was actually metasediment, so I assume the manganese was high already before the metamorphism, so that's why the chloride is also high in manganese. But this was both of them, like all of this rock was originally the same stuff, which is tholeiitic metabasalt, but the way that they have this kind of trending pattern is, I believe this is because of the alteration before the metamorphism. And then this is the garnet data that we analyze. So we have this kind of a nice trending pattern. So generally, if you have garnet associated with the massive sulfide mineralization, you will have manganese enrichment in garnet. But as you go towards the hanging wall stuff, you will have calcium enrichment because of the seawater alteration stuff. So this is the trending for the hanging wall. This is the trending for the massive sulfide. And then from the rare earth pattern as well in garnet, we can see that garnet associated with massive sulfide mineralization will characterized by this strong positive European anomaly, whereas garnet from hanging wall and regional garnet, regional metamorphic garnet, usually just like doesn't show any like positive European anomaly, basically just like a normal metamorphic garnet. And then this is what we found in Gerloch. Apparently, all those garnet is plotted within the hanging wall trending, even the one from the footwall. And then if we're looking at the rare earth element, it's also very typical of a metamorphic garnet, not really associated with the massive sulfide, except for the one from honorary-basite that has a strong positive European anomaly, which is really interesting because this is not part of the exploration target at the moment. And then we also done a little bit of amphibole geochemistry. And from amphibole geochemistry, there are not much study from this mineral, but generally it has the same signature as garnet. If it's associated with mineralization, you will have positive European anomaly. And this is the results from the amphibole, basically. And interestingly, we find this, if you still remember the one from chloride, it has the same trending pattern. And then in terms of manganese, drop in hanging wall. And this confusing units, I would say, has also like slightly higher manganese content. So kind of makes sense, but we're still not sure why they behave something like this. And from the rare earth element patterns, as I said, everything just very normal metamorphic amphibole, except again, the one from honorary-basite, which has strong positive European anomaly. So again, it's a thing, probably, but we're not sure. And I'll probably, because I don't have much time, but I'm gonna go through quickly from the geophysics, especially field magnetic survey from one of undergrad student that done this survey recently. So Arthur did a field magnetic survey across the region using GM system over Hauser magnetometer. So he's carrying something like this instrument and walk along this region to record the magnetic anomaly across the region, just basically to map any magnetic anomaly. And then this is some of the results, basically this region. So the yellow is the magnetic anomaly. And then if it's blue or green, it's basically like less magnetic. So it's not mineralized or it's not iron rich. And then if we overlay this with the geology, so the red here, the red circle here is actually the massive sulfide lens outcrop that I showed you earlier. And then this is also another massive sulfide outcrop nearby. So this is kind of consistent. So it has strong magnetic anomaly. And then this really high magnetic anomaly is actually the ironstone. So it's kind of consistent, basically. And then he also go through several area. This is basically just bunch of amphibolite. So that's why it's kind of quiet magnetically. And then in this region also has a little bit of a anomaly here. And Arthur interpret this as a BIF or ironstone. And then interesting region is probably near this law down here, which has a really strong magnetic anomaly, basically. And if we zoomed in, here we can see that it has really strong anomaly here, which is associated with the BIF. But here, again, if you remember from the previous slide, where you in this belt you have BIF, and this bit is usually the massive sulphide. And then, well, we're not really entirely sure whether is it BIF, another BIF or massive sulphide, but the geometry of the anomaly is kind of lens shape, which is a very typical of massive sulphide mineralization. So it could be massive sulphide, but it can be also BIF. We can't really distinguish which one is which. But the BIF trend is right here. So this may be the ore body, maybe. So yeah, as a summary, the Kerry Road is a mafic-hosted metamorphosed VMS deposit. The hanging wall is mostly amphibolite with calcite quartz chloride alteration. The footwall is also mostly amphibolite with a slightly different alteration. And all those amphibolite is basically tholeiitic basalt in origin, whereas we also have a little bit of meta sediment in the deeper part of the stratigraphy. And then manganese content in chloride and amphibole systematically increased toward the massive sulfide mineralization. And we also found positive europium anomaly in garnet and amphibole from the honorary bayside, which probably suggests strong prospectivity. And magnetic survey also reveal some lenticular anomaly, which potentially is sulfide ore body. And this could be a good mineralization target. And yeah, and this is some of the photo that during our field work, and this is some of future works that we're gonna do to complete this project, basically. Thank you.